So in this lecture, I'm going to finish up talking about Markov measures and show their ergodicity and mixing properties under certain conditions. So I'll start by reminding you of the definition. So we have a stochastic matrix, and that means it's a non-negative matrix, and the row sums are all equal to 1. And we're going to assume that it's irreducible. So that means for every position, there's some n for which the nth iterate at that position is bigger than 0. This is equivalent in the graph picture to there being some path between I and j of length some n. And this implies by Perron-Frobenius theorem that there's a unique left eigenvector which is in fact bigger than 0 and it has eigenvalue 1, or it satisfies this formula here. And given this equipment, or given this data, we can assign a Markov measure on cylinder sets by, here's the definition. We have first the probability of being in the first state, the B0, and then the matrix is giving transition probabilities. Transition between B0 and B1 has this probability, etc., all the way down till we finish the element. All right, so notice there's no m in the formula here, so that makes it shift invariant when we extend it to the entire Borel algebra. So here I just explained what I just went through in words, that the probability of this finite sequence occurring, thinking of this as a sequence of states in a Markov process, you have a probability of starting at B0, and then you have next the probability of the first transition, second transition, all the way down to the final transition. So here's the theorem about the ergodicity and mixing. If you have an irreducible stochastic matrix or transition matrix, then you get an ergodic measure went through this construction. And if in addition you have a primitive, in other words, there's some uniform n for which the entire nth iterate is positive, then it's mixing, or as sometimes said, strong mixing. So there's two lemmas, so most of the work is in proving the two lemmas. The first is that we're going to have a stochastic, that if you have an irreducible matrix and you have this left eigenvector and this relation for eigenvalue 1, then this Birkhoff type average converges to, first it converges, but what it converges to is a kind of degenerate matrix, all of whose rows are P. All right, now if you have a stronger condition that it's primitive, then the nth iterate, in fact, converges to P, not just in average like this, but actually converges. So this one is part of the Perron-Frobenius theorem. This one could be, but it's not in the usual statements, so I'm going to prove it at the end. So the second lemma has to do with the measure of the intersections of cylinder sets. So here's a cylinder set starting at L. Here's a cylinder set starting at K. When we find the measure of their intersection, well, we have a term here that looks like the measure of the first guy. We have a term here, which we'll see corresponds to the transition probability from M to B0. And it takes K minus L steps to get there. And then we have all the transition probabilities corresponding to the second cylinder set. So K here is to the right, so the picture looks like one of these guys is down here and the other guy is way up there in terms of what's restricted. So here's the proof. So what we have to do is check on cylinder sets, so that was the previous theorem that I stated but didn't prove. You have to show that this intersection of B with consecutive inverse iterates of C has to converge on average to the product of the probabilities. So this, or product of the measures. So this suffices for ergodicity and this suffices for mixing. All right, so this implies that, as you should remember. All right, so how do you prove this given the lemmas? Well, the first thing is to notice that, where'd that formula go? That when we have this product here, what we're missing to get the measure of this guy is the probability of B0. So we put that in the denominator. All right, so we take lemma 2 and we rewrite it as the measure of the first times the measure of the second. But then there's this transition probability, as I'll discuss later, from going from one cylinder set to the other cylinder set. All right, so here's what we're doing. So let's say we have a pair of cylinder sets here. I changed the names here just because we've used A for the matrix. So B is this cylinder set. Then when we shift by sigma to the minus n of C, that's what we have to do to check this condition here. We just move it to the right by n. And we can pick n large enough so that we're in this picture. We can pick n large enough so we've pushed this so there's a gap between them. And then the gap between them, we know, looks like, it gives rise to a term like this. That's my first observation. There's the measure of B, the measure of this inverse image of C, and then this transition term. Now the two things we need now is that first, this is an invariant measure, so this measure is the same as mu c. And the second thing is that this term here goes to P of B naught. So that's implicit here in this statement here. It's going, and we're looking in the B naught column here. And so it's converging to that. Ergodicity is similar, but you just have sums and averages. Okay. So let's see the proofs of these lemmas, 1 and 2 here. This is primarily algebraic, but we're going to use the Ergodic theorem, and this is basically the definition of the measure. So let's first try to understand lemma 2 by kind of a simple example, or a concrete example. I don't know how simple it is. So let's look at the intersection. So here's one cylinder set starts at 0, and the other cylinder set starts at 3. And so what that means is we've nailed down places 0 and 1, and we've nailed down places 3 and 4, but there's a star here because there's a gap between what's nailed down by the two cylinder sets. So we have all possible sequences where this star is either here a 0, a 1, or a 2. Now the key idea to understanding how to compute the measure of such a thing is to write it as the disjoint union of, in this case, length 5 cylinder sets. So that just corresponds to nailing down what happens here. All right, so this intersection is equal to what we get when we put a 0 here, what we get when we put a 1 here, and what we get when we put a 2 there. All right, so that tells us that the measure of this intersection is equal to the sum of the measures, because it's a disjoint union. And each one of these, we just use the formula for the Markov measure. And so we get this P1, A1, 0, and then we go from 0 to I, from I to 2, then from 2 to 0. So these terms occur in all the terms, so we bring them outside, and we're left with this guy here. So if you've done some fair amount of linear algebra, this should be familiar. You have repeated indices here together, if you know tensor notation. But if you just look at matrix multiplication, if you do the 0th row times the second column, you get exactly this sum. All right, so this says, again, this is basically matrix multiplication, that this sum in this measure is actually just a squared from 0 to 2, the 0 coming from the last entry here, and the 2 from the first entry here. All right, so we can rewrite our formula that the measure of this intersection is P1, A1, 0, and then we get the square and the entry 0, 2, and then 2, 0. All right, so just to make sure we understand, let's shift the second one over. And so now we have two places to fill in. And if you compute, you get this. And then from the disjoint union, you're going to get a sum over I and j, because we have two places to fill in. We put an I in one. Then we have a double sum. And now we look at what this guy is. And this guy, in fact, is the third iterate between 0 and 2. All right, so here's a basic linear algebra fact that if we look at a sum like this with the sum over all possible ij's, then it's equal to, here's the a, here's the b, the sum over all these repeated indices, you get a to the k, a, b. All right, so that's a straightforward induction. All right, but I wanted to investigate a little more about what this means in terms of transition probabilities. Let's go back to the sigma 2 example, where we have these and these, or if you like, this sum here. Where'd the sum go? This sum here. Now, what's the meaning? Well, the probability of going from 0 to 0 is A0, 0. From 0 to 1 is A0, 1, A0, 2. And then from 0 back to 2 is A0, 2, A1, 2, A2, 2. So if you look at the sum of the probabilities of getting from 0 to 2, you have three paths to do it on, each one corresponding to product of these terms. And so this sum is the transition probability in 2 steps. All right, so the general fact is then that if you take the kth iterate and look at the AB entry, it's the transition probability from A to B in k steps. Now, if you're thinking of this as a graph, it's a length k path in the graph. All right, so that's the meaning of this kth iterate, a certain entry. It's the transition probabilities in k steps from A to B. All right, so let's look at this example. Again, if we look at this measure, it's the probability of starting at 1, and then you transition from 1 to 0, and then you transition from 0 to 2 in 3 steps, right? Because there's a gap here, you have to go 1, 2, 3 to get there. And so that gives this 8 cubed, and then you have the probability from 2 to 0. All right, so let's actually prove this. So given what we understand now, the proof is easy. I'm going to nail down the first cylinder set at 0, just so I have one less symbol to run around. Well, the proof is exactly what you'd expect. So k is big enough, so there's a gap here, that this intersection is this disjoint union. Now, where we fill in this gap, here I indexed them with m to k minus 1, just so I didn't get mixed up with shifting these down to 1 and 0. Right, and these are where these are all possibilities. And then we translate this into measures. When measures, we get a sum. All right, and so this continues on here. So this continues on here. And then by lemma 3, we replace this with the AM being the last one here to the first one here. And so this is the number of iterates we need, the number of steps to get from there to there. All right, so the actual proof is pretty easy, but it's kind of mysterious formulas. But once you understand in terms of transition probabilities, it's pretty easy. All right, so now I have to go back and prove lemma 1. So let's go back here and find lemma 1 here. So lemma 1 is about the iterates of n, of A. So remember, you could think about these as the transition probabilities for longer and longer paths from one state to another. And this is stating that if it's primitive, then it's converging to a nice steady state. And here it's converging on average, where the steady state is characterized by these probabilities that are the invariant probabilities in terms of this. All right, so let's see how to prove that one with the average. Uh-oh, I seem to be dead here. All right. All right, so we have to work with this sum, which, as I said, looks like a Birkhoff average or a Cesaro average, but now there's not a function here. We're just iterating A. So here's a trick that's useful for getting from transitions to symbols and functions to symbols and ergodic theorem to symbols. So let chi j be the indicator function of the cylinder set 0j. So this is just a length 1. All right, so this is just the cylinder set, which says in the 0th place you have to have a j. And just to make life simple, we don't, this is its indicator function. All right, so the pointwise ergodic theorem tells us, well, we know we have a measure preserving transformation here. And so the pointwise ergodic theorem, just the general one, tells us that this sum converges to this almost everywhere. All right, so there's some function here in L1 for which this converges almost everywhere, and now everything is when almost everywhere it means with respect to the Markov measure. Now we use the trick we used before. We multiply by chi sub I, so for another indicator function. And as we proved before, this guy, this product, is bounded above by 1. And so the bounded convergence theorem says that now this integral here converges to this integral here. So we've multiplied both sides by chi I and then integrated. And of course, it's a finite sum, so I brought it inside. This is an I here. All right, but notice what this integral actually is here. All right, so what this integral actually is here is, well, I rewrote it here, but this is a product of indicator functions. And this guy, this is the indicator function of remember, this corresponds to the cylinder set J. And so we've seen this trick before, that this corresponds to, when you bring this down, you get an inverse. So this is actually the indicator function of sigma to the -1 of J of the cylinder set J intersect I from this term, the cylinder set I. And of course, this is an indicator function. When we integrate with respect to measure, we get its measure. All right, but you go back what we proved about the measure of a intersection of cylinder sets. This is the simplest case. We, in fact, because these are just length 1, all we get is pi times a to the n, and then the transition from a to j. All right, and this is when, of course, n is bigger than 1. So we actually used that previous lemma. All right, so what have we shown? We've shown that this integral converges, but this integral is actually p sub I a to the n to the ij. All right, so this tells us that a to the I to the nj actually converges to this quantity here, right, which is therefore, I'm going to call q to the ij. All right, so that's convergence of this thing on average, because remember this integral here, this wasn't just the integral, it was the average of it. All right, so we get now at least a pointwise limit or a matrix limit. There's no function here, so this limit exists almost everywhere. Right, sorry, cancel the almost everywhere. This limit just exists. This is a matrix, no longer a function. And we have a formula for these, which turn out we're not going to use. All right, now what else do I need to show to finish the theorem? I have to show that Q is in fact this very special degenerate matrix. All right, so now we've assumed we haven't really used irreducible, but here's where we pull out irreducibility. So irreducibility, there's this unique positive eigenvector for the eigenvalue 1 from the left. Now notice that Q times A is, we just get an extra A here. Remember, Q is just this this average here, this limit of these averages. And so we get an extra A here, and then we showed, so this is a standard trick that if you increase the power here, you get the same limit on average. That was lecture 9, page 10. All right, so we get QA equals A. All right, now think about what that means row by row. It means if you have a row of Q, then that row times A gives the same row of Q. All right, so in terms of rows, we get RIA equals RI. So R sub I is just the name I gave to the ith row. And so we know that R sub I is a left eigenvector with eigenvalue 1. Now, that doesn't mean it's equal to P. It could be a multiple of P because, eigenvectors aren't unique. They're just unique up to scalar multiple. All right. Now, this P was characterized by it having sums of its entries equal to 1. All right. Maybe I should have been adding that somewhere, that the sum of P sub I is equal to 1. All right, so there's a unique such thing. So what I need to show finally to finish is that the sum of the entries of Ri is 1, so that it's normalized correctly. All right, so that's pretty easy. A is stochastic, and so A to the n is stochastic. Then when we compute this sum, we get the sum of capital N stochastic matrices. So the sum has row sums equal to n. When we put the averaging in, we get that this is stochastic, and then the limit of stochastic matrices is also stochastic since, row sum is continuous. And so that means that Q has row sums equal to 1, and so it must be the matrix that we claimed it was.